Look around you. Everything you see should not exist. According to our best theories, the universe should be completely empty. Not empty like an empty room, empty like nothing, just light sailing through the void forever with nothing to receive it. Yet here we are, made of atoms that the equations say are impossible. Either our mathematics is fundamentally broken, or something extraordinary happened in the first moments of existence, something brief, violent, and still not fully explained. Cambridge, 1928. Paul Dirac is trying to write an equation for electrons that respects both quantum mechanics and Einstein's relativity. He succeeds in 2 months, producing an elegant equation that automatically predicts electron spin and explains hydrogen's fine structure perfectly. But the equation has an unwanted feature. When you solve it, you get 2 solutions. One describes electrons, the other describes particles identical to electrons, same mass, same spin, except with positive charge instead of negative, a mirror particle, an anti-electron. Dirac tried to explain this away. Maybe these are protons. No, protons weigh 2,000 times more. These mirror particles had to match the electron's mass exactly. In 1931, Dirac made his prediction. A new particle exists, identical to the electron, but positively charged. If you bring an electron and anti-electron together, they annihilate completely, converting all their mass into pure energy. Gone. Pure mathematics was predicting something no one had ever seen. 1 year later, reality confirmed it. 1932, Caltech. Carl Anderson, age 27, is studying cosmic rays with a cloud chamber, a device where charged particles leave visible trails in vapor. Add a magnetic field, and the trails curve based on charge and mass. Anderson photographs a track that curves like an electron, but bends the wrong way, as if it has positive charge. He has a lead plate in his chamber, and he can see the particle loses energy passing through, because the curvature increases afterward. No escape. This is a positively charged particle with an electron's mass, the positron. Anderson wins the Nobel Prize in 1936. Dirac had won his in 1933. Dirac's equation was not unique to electrons. Its structure implied every particle should have an antiparticle, and this proved correct. Antiprotons in 1955, antineutrons in 1956, eventually the entire zoo. Nature has a complete mirror. For every particle of matter, there is antimatter with identical mass but opposite charge. Beautiful, symmetric, but disastrous for cosmic history. Go back 14 billion years to the Big Bang. The universe is unimaginably hot and dense. Energy constantly converts into particle-antiparticle pairs. Electrons and positrons flash into existence and annihilate billions of times per second. Quarks and antiquarks appear and vanish in absolute frenzy. Always in pairs. You cannot create a particle without creating its antiparticle. This is law. As the universe expands and cools, eventually there is not enough energy to create new pairs. Creation stops, but annihilation continues. Every quark finds an antiquark. Every electron finds a positron. They destroy each other. If matter and antimatter are perfectly symmetric, every single particle should find its antiparticle and annihilate. Complete destruction. The universe should contain nothing but photons. The ledger should equal 0. Obviously, it does not. You are here. Something broke the accounting. Maybe the antimatter is just far away. Perhaps there are antimatter galaxies across the universe made of antiprotons and positrons. They would look identical to our galaxies because antimatter emits the same light as matter. But this fails immediately. The universe was not always so spread out. At boundaries between matter and antimatter regions, particles would meet and annihilate, producing gamma rays with very specific energies. We have looked with every gamma-ray telescope available. We see nothing. No boundaries exist. The antimatter is not separated. It is gone. Almost all of it was destroyed, along with almost all of the matter. What we observe today is merely the tiny residue that survived. How tiny? For every billion antiparticles in the early universe, there were 1,000,000,001 matter particles. One extra, 1 part in a billion. That single extra pair per billion is everything you have ever seen. The other billion pairs annihilated perfectly. You live in the leftovers. To answer this, we need to understand symmetry as physicists define it. Imagine watching particles interact. Now put on special glasses. The first pair shows you the mirror image. Left becomes right. This is parity, labeled P. If physics looks identical in the mirror, parity is conserved. A second pair of glasses replaces every particle with its antiparticle. This is charge conjugation, labeled C. If physics looks identical after this swap, C is conserved. For decades, physicists assumed both symmetries held absolutely. Why would the universe distinguish between left and right? Why treat matter differently than antimatter? Then 1956 shattered this assumption. Two theorists, Li and Yang, noticed puzzling data in certain particle decays. They proposed something scandalous. Maybe parity is not conserved. Most physicists rejected this. Wolfgang Pauli publicly stated he would bet large sums that parity must be conserved. He lost. Chien-Shian Wu designed the test. She used cobalt-60 nuclei, which spin like tiny tops. When they decay, they emit electrons. She cooled her sample to near absolute zero and aligned all the nuclear spins with magnetic fields, and then watched which direction the electrons emerged. If parity were conserved, electrons should emerge equally in both directions, symmetric. They did not. Electrons emerged preferentially in one direction, clear asymmetry. Parity was violated. The mirror was broken. Li and Yang received the Nobel Prize in 1957. Wu shamefully did not share it. Almost immediately, physicists noticed charge conjugation, C, was also violated. The weak force treats particles and antiparticles differently. Both mirrors were cracked.
But theorist Lev Landau proposed something clever. Maybe C and P are broken individually, but if you apply both simultaneously, swap particles for antiparticles, and reflect space, perhaps then physics looks the same. The combined operation, CP, might still be perfectly symmetric. For years, every experiment confirmed this. CP symmetry appeared exact. This mattered enormously, because if CP is exact, matter and antimatter are truly identical. Every process creating a proton creates an antiproton at exactly the same rate. You can never generate excess matter. The ledger always balances to zero. To get our universe, CP must be broken. Nature must cheat in favor of matter. Does it? 1964, Brookhaven National Laboratory. James Cronin, Val Fitch, and colleagues study neutral kaons, particles that oscillate between particle and antiparticle states before decaying. Neutral kaons come in two versions:
Short-lived ones decay quickly into 2 pions. Long-lived ones survive longer and decay into 3 pions. If Cp is exact, this separation is absolute. Long-lived kaons are strictly forbidden from decaying into 2 pions. Not unlikely, impossible. They built a 57-foot beamline, produce kaons, let them travel. By the far end, all short-lived kaons have decayed. Only long-lived ones remain. Then observe their decays. If Cp is exact, you should see only 3 pion decays, 0 2 pion decays. They saw 2 pion decays, about 2 in every 1,000. Tiny but unmistakable. Cp symmetry was broken. The universe is not fair. Nature does cheat. Cronin and Fitch won the Nobel Prize in 1980. The door was open. In 1967, Andrei Sakharov asked what minimum conditions must be met to produce excess matter over antimatter. He identified 3 requirements. First, baryon number must be violated. Every proton counts as +1, every antiproton as -1. If this is always conserved, you create equal numbers. Something must break this rule. Second, C and Cp must be violated. Otherwise, every matter-producing process has a matching antimatter process at the same rate. Third, these processes must occur out of thermal equilibrium. In equilibrium, forward and backward reactions wash out any asymmetry. We know Cp is violated. Experiments proved it. Departure from equilibrium is plausible in the expanding universe. Baryon number violation likely occurs at very high energies in the early universe. All 3 conditions can be met. The framework exists. But here is the devastating problem. When you calculate how much asymmetry the standard model produces, you get a number about 10 billion times too small to explain what we observe. The standard model gives you a preference for matter, but nowhere near enough. It is like finding a 1 millimeter crack in a dam and looking at the flooded valley downstream. The crack explains the water's direction, but not the volume. Something else happened. This is powerful evidence the standard model is incomplete. When you ask it why there is something rather than nothing, it gives you an answer 10 billion times too small. New physics exists, physics we have not discovered yet. Several possibilities are being pursued. Neutrinos might hold the answer. These ghostly particles barely interact with matter. There are theoretical reasons to believe Cp violation exists in the neutrino sector. There may have been heavy partner neutrinos in the early universe whose decays produced more matter leptons than antimatter. Experiments are underway to measure this. Another idea involves heavy particles that existed briefly in the early universe but have since decayed asymmetrically. A third possibility concerns the electroweak phase transition, when electromagnetic and weak forces split apart. If this was a first-order transition with expanding bubbles, the bubble walls could have provided the conditions needed for asymmetry generation. Each possibility points beyond the standard model. During the first microseconds, there were 10 billion antiquarks for every 10 billion and 1 quarks. Those 10 billion pairs annihilated completely. The one leftover quark had no partner. It survived. Those survivors formed every atom you will ever touch. Today, we measure 6 baryons for every 10 billion photons in the cosmic microwave background. That ratio is the fossil record of annihilation. Those photons are ghosts of destroyed matter and antimatter. The baryons are the remainder. You are a rounding error from a catastrophe. We know antimatter exists. We manufacture it daily in accelerators. We know the early universe produced enormous quantities of both that nearly completely annihilated. We know a tiny asymmetry, 1 part in a billion, tilted the balance. This is why anything exists. We know CP symmetry is broken. Experiments proved it. We know Sakharov's 3 conditions. We know the standard model CP violation is insufficient by 10 billion times. And we do not know what new physics is responsible. We do not know if the answer lies in neutrinos, heavy particles, or something unexpected. But consider this. In 1928, we didn't know antimatter existed. By 1932, we found it. By 1964, we knew symmetry was broken. By 1967, we had a precise framework. In 40 years, we went from ignorance to a clear checklist for existence. The missing piece will reveal something profound: new particles, new forces, a new sector of reality. The matter-antimatter asymmetry is a window into the unknown, and we know where to look. The universe produced 1 billion antimatter particles for every 1,000,000,001 matter particles. The billion pairs annihilated. 1 survived. That 1 became everything. If the universe were perfectly fair between matter and antimatter, nothing would exist, just light forever. What does it mean that existence depends on broken symmetry? What does it mean that the universe is slightly unfair? There's a mechanism. We don't fully understand it yet, but there are rules. Those rules generated the asymmetry that allowed you to exist. Our job is to find them.